Last video we are looking at the Frobenius solutions for the Bessel equation, and we looked at the case 1, that is difference between the roots of the initial equation is a non-integer. This video we will see a difference is integer case. Okay. So, we have seen in the last video and the roots difference is non-integer, and you found two solutions, one is y1 and y2, and you multiplied some certain constant to y1 and you defined what is called a Bessel function of first kind, that is j alpha of x. So, in that what is the constant involved, gamma function, so that you might not be knowing. So, let us discuss about what is a gamma function. So, we have a gamma function. So, gamma function. So, its definition is so definition of gamma function is defined for all complex numbers as integral 0 to infinity power minus x power z minus 1 dx. So, this is what you have, and real part of z is positive. Okay. So, this is what it is. So, if you actually, so pictorially if you look at it, if you see this is defined everywhere whenever real part of z is positive. So, everywhere. So, that means including we are interested only for the gamma function for real values. So, the way it's defined, it's defined for all x positive. Okay. So, when x equal to 0 if you put, then this integral what happens, gamma at 0 x equal to 0, this is the integral. So, e power minus x by x dx. So, this is actually certainly infinity. So, because of this point is not defined. Okay. Now, we look at the property of gamma function, that is if you calculate this for at z plus 1, then what you get is e power minus x power z dx. Do the integration by parts, then you see that e power minus x power z x power z. So, the limits 0 to infinity minus plus 0 to infinity e power minus x z into z comes out because just constant z into x power z minus 1 dx. So, this is nothing but, so you can see at infinity e power minus x goes to 0. So, 0 x power z is 0. So, you have this terms does not contribute. So, you have z times what you are left with is simply a gamma function. So, this is your property of gamma function. So, if you use this, what we see is that we are interested to see what are all the values of negative real numbers for which gamma function is defined. Okay. So, you see that is 0 at 0 positive 1 it is defined. Okay. It is of course including 1, everywhere it is defined this side. So, 0 to 1. So, you take gamma z, I am defining here in the negative side, at 0 it is not defined, 0 to minus 1. So, gamma z equal to, so you take from here gamma z is gamma z plus 1 by z. So, 1 by z times gamma z plus 1, when z is here, z plus 1 be here, okay, which is well defined. So, z plus 1 is well defined, z you take as a negative numbers between minus 1 to 0. So, gamma z plus 1 by z is well defined in minus 1 to 0. Okay. Again, once you know this gamma z in minus 1 to 0, now you know everything here. Now, you can define minus 2 to minus 1. So, again in minus 2 to minus 1, if you take z plus 1 be here, which you have seen already. Okay. By iterative like this, iteratively you can go on defining everywhere, every single interval of length 1 except these negative integers. Okay. Except these negative integers including 0, you do not have gamma function defined there. Okay. So, everywhere else it is defined, that is what is important. Okay. So, let us see what is the last video we have defined what is a gamma function. And gamma function what we Bessel function of first kind we defined in the last video, that we will see. So, j alpha of x is x alpha by 2 power alpha gamma of alpha plus 1 times 1 plus sigma m is from 1 to infinity minus 1 power m x power 2m by 2 power 2m m factorial. Now we have here alpha plus 1, alpha plus 2 up to alpha plus m. That is what you have. Now you can see that gamma, so use this property. If you use this property here, so if you use this, alpha plus 1 into gamma alpha plus 1 is gamma alpha plus 2. Again alpha plus 2 into gamma alpha plus 2 is gamma alpha plus 3. So finally you take with alpha plus m into gamma alpha plus m will be gamma alpha plus m plus 1. So if you do that, x power alpha by 2 power alpha, that is a common. So you have take it inside here 1 divided by gamma of alpha plus 1, and here you can club this gamma with this, so that what you end up is minus 1 power m 2 power x power 2m by 2 power 2m m factorial. Here gamma of alpha plus m plus 1. Okay. So this is what is Bessel function of first kind. Okay. So now we look at the case of second case, when the difference between the two integers 2 alpha is k1 minus k2, which is 2 alpha, alpha minus of minus alpha, so which is an integer, okay, which is an integer. So 2 alpha is always positive, so it's which is a positive integer. Non-integer case we have seen in the last video. We will see how what is now for every integer case. So and 2 alpha is integer means 2 alpha is either 0 case we will deal separately in the next video. So 2 alpha is 1, 2, 3, 4 and so on, okay, 4, 5, 6, 7 and so on. So you look at this case when 1, 3, 5, 7 all odd integers, alpha is 1 by 2, 3 by 2, 5 by 2, 7 by 2 and so on. Okay. So you can look at this one. So this gamma function, gamma of alpha is half or 3 by 2 or anything. So half of odd integer plus m plus 1 is still never be negative integer, okay, whatever may be the case. This will always be positive, so it still is well defined, right. Even if I choose alpha as negative, that is even if, so what I mean to say is let us take j minus alpha, just replace alpha by minus alpha. What you have is j alpha by 2 power minus alpha is 1 by gamma of minus alpha plus 1 plus 1 sigma m is from 1 to infinity x by 2 power m divided by m factorial gamma of minus alpha plus m plus 1. Okay. So when alpha is one of these values, this gamma of minus alpha plus m plus 1. So you can see that gamma of, let us say take 5 by 2 minus 5 by 2 plus m plus 1. This can be a negative number when m is 1, okay, but this never be a negative integer, okay. So this is never be one of these values, especially when alpha is this one. So that means from the recurrence relation of the Bessel equation, if you simply replace k1 k by k2, that is minus alpha, you do not have issues to find, you do not have problem to find the constants. Those constants you will get it without a problem, because this gamma function is well defined. So what you get is the same number with alpha is replaced with minus alpha, and you replace alpha by minus alpha if this becomes 0, but this cannot be 0. This is not a problem, because this is it's not even defined at these values, and when alpha is a negative integer, 2 alpha is a negative integer, so 2 alpha is odd integer, sorry, okay, when 2 alpha is odd integer, that is alpha is half, 3 by 2, 5 by 2, 7 by 2 and so on. This gamma function when alpha is replaced with negative minus, so this one is never be negative integer and it is well defined, this is well defined. So you will be able to find all the coefficients, so that finally you end up the solution like this with some constant. Now I replaced in the gamma function as x power alpha by 2 power alpha into gamma alpha plus 1, with alpha being minus alpha, x power minus alpha divided by 2 power minus alpha gamma of minus alpha plus 1. With that constant you multiply, what you end up is this same Bessel function of first kind, but for minus alpha. So, this is well defined. So, what you have, this is another solution, this is the second solution. That means, you do not have problem when it is odd integer, odd integer case you do not have problems, you can get the second solution directly from the recurrence relation, because I do not have problem with this 1 by 0 or 0 by 0 when you try to calculate those constants in the power series. Only trouble with this, so only when 2 alpha is 2, 4, 6, 8 and so on. So, that is, so we are left with only one case, alpha is 1, 2, 3 and so on. Okay. So, actual integer. So, or you can write alpha equal to n is from 1, 2, 3 onwards. So, this is what is we are interested. So, this is actually case 2. Case 2 is actually only about this. Okay. So, we have seen Jn of x is one solution. So, you have x power n divided by 2 power n 1 by gamma when alpha is n, it is gamma n plus 1 is n factorial plus sigma m is from 1 to infinity minus 1 power m x by 2 power 2 m divided by m factorial. Here gamma of n plus m plus 1, that is n plus m factorial. So, this is what is your Jn, Bessel function of first kind. This is one solution in this case, which you always get when for the bigger root of in the Frobenius method. Of course, you multiply certain constant, conventional constant to define this solution as a Bessel function of first kind. So, the second solution in the Frobenius method, you should look for y2 of x. y2 of x, I define it as this way. So, you look for solution in this form. Y1 is my Jnx, I take it as Jn of x log x plus x power minus n, k is from 0 to infinity I dk x power k. So, this is simply dummy, k is a dummy variable. I look for solution in this form. For this I need to substitute into the equation x square y double dash plus x y dash. This is the Bessel equation, plus x square minus alpha is n, x square minus n square y equal to 0. So, in this I need to substitute y2. Okay. So, this is actually satisfying y2. So, if we look for solution in this form, substitute this Bessel equation and try to get your unknown constants a and dk. Okay. That is the idea of the Frobenius method. So, you need y2 dash. So, y2 dash of x is a by x. So, you are differentiating two functions, product of two functions. So, you do that. So, a by x Jn of x plus a Jn dash of x log x plus minus n x power minus n minus 1, and this series as it is x power k plus x power minus n, k is from 0 to 1 to infinity. So, k dk x power k minus 1. Okay. That is what is your y2 dash. Now, y2 double dash you calculate again. So, what you see is minus a by x square jn x plus a by x jn dash of x. So, here when you differentiate log x, you get the same term. So, you have a 2 plus a times jn double dash of x log x. Okay. And this one, and then what you have is minus n into minus n minus 1. So, it will be plus n into n plus 1 x power minus n minus 2 sigma k is from 0 to infinity dk x power k minus n x power minus n minus 1, and this is running from 1 to infinity k dk x power k minus 1. Now, we differentiate the last term, that will give me minus n x power minus n minus 1, k is from 1 to infinity k dk x power k minus 1 plus x power minus n. This is running from 2 to infinity k into k minus 1 dk x power k minus 2. So, this is what is the two derivatives. Now, we put this into this Bessel equation to get finally. So, see that what you get is substitute into the substitute into Bessel equation. Y double dash plus xy dash plus x square minus n square y equal to 0 to get what you get is minus a. So you are multiplying x square for y2 double dash. So minus a jn 2ax jn dash of x plus ax square jn double dash of x log x plus n into n plus 1 x power minus n, k is from 0 to infinity, dk x power k minus n into x power minus n sigma k is from 1 to infinity k dk x power k. So I have taken my 1x here, 1x here. So and then minus n x power minus n, again k is from 1 to infinity k dk x power k plus x power minus n sigma k is from 2 to infinity k into k minus 1 dk x power k. Now this one plus x times y2 dash, so that is a jn of x plus a x jn dash of x log x minus x power minus n, k is from 0 to infinity dk x power k plus x power minus n, k is from 1 to infinity k dk x power k. So that's my second term in the here. Now plus x square minus n square, and you have this that is the term a jn of x log x plus x square minus n square sigma x power minus n, right? So you have x power minus n sigma m k is from 0 to infinity dk x power k equal to 0. So this is what I substitute into this. So from this relation I should get all my constants a and dk's. That's from the Frobenius method. That's what we will see now. Okay. So if you simplify further, so you first simplification you can see this one. So you add this one, look at these three terms, this one and this one. This is exactly the Bessel equation. Bessel equation, left hand side of the Bessel equation. So because a is common, jn of x is satisfying the Bessel equation. So this sum of these three terms is 0. Okay. So they won't contribute here. So what you are left with is, so I will see also you can cancel these two terms and you are left with this term. Okay. So you write this 2ax jn dash of x. Now each of these series you just pick up common terms, so it's a common index, that is 2 to infinity. Okay. So if I write this from k is from 2 to infinity, so and then what you can take x power n inside. So what you have is this is what you have. So you have dk x power minus n plus k. So wherever you have picked up these things, so n into n plus 1, okay, first from here, and then you have a minus nk and plus nk. So you have a minus 2 nk. So you have minus nk and I have another one here. Okay, and then here plus k into k minus 1, and then here minus n and plus k. Okay, and then what happens to this term? So this term again you have minus in this second term, so you have a minus n square. Okay, so and then what you are left with is only the terms that involves 0 and 1. So you have a 0 here. So before I see this, I will take x square. So and you write this x square x k is from 0 to infinity dk x power k plus 2. So if if I put together this term with x square multiplication, this you can rewrite by replacing k equal to k minus 2. So it is actually running from 2 to infinity, k equal to k minus 2, so that this becomes this. Okay. And I have what I am left with is only the terms with k equal to 0 and k equal to 0 if you choose k equal to 0 here. So this is the term n into n plus 1, and then k equal to 0, where else you have here? You have here minus n, and again here. So you have a minus n square. Okay. So this is simply 0. So that is 1. So k equal to 0 terms are not there. And now k equal to 1. K equal to 1 terms, you calculate. So n into n plus 1 here, and then minus n, k equal to 1, and so minus 2n actually here. Okay. And here again minus n. Okay. And then k equal to 1 here, so plus 1, and here. So you have finally minus n square, that is for d1. So this is corresponds to into d1 x power minus n plus 1. So you have what you are left with is n square goes, plus n minus n goes. So what you are left with is 1 minus 2n. So you finally end up with 1 minus 2n d1 x power minus n plus 1 equal to 0. d1 equal to 0. So this is what is n? N so far is running from 1, 2, 3 onwards. So n is actually 1, 2, 3 onwards. So this is the equation. So now whole equation is this. Now because now you can substitute what is your Jn of x, okay, Jn dash. So for this you need Jn, you know Jn, you calculate Jn dash. Jn dash if you calculate, and you can get what you get Jn dash. So you can just get this term, okay. From this you calculate Jn, I am writing directly. So this is your Jn, you differentiate this Jn and then try to substitute. So you will get 2ax Jn dash of x will be an x power n divided by 2 power n minus 1 by n factorial plus a times sigma m is from 1 to infinity minus 1 power m 2m plus n x power 2m plus n divided by 2 power 2m plus n minus 1 m factorial m plus n factorial. So you can directly see this is not difficult. You simply calculate Jn dash and multiply with 2ax. This is what is the result. Then plus you have this k is from 2 to infinity. Now if you calculate this one, if you just see this, n square goes, k minus n and plus n goes, and what you are left with is minus k goes, and k square. So you have a k into k square minus 2nk. So you have again k minus 2n. So k square and k to n is this one. So into dk x power minus n plus k. So you can put it together. And I think I missed here in this x square into this one, I have missed minus n. So you can put it together these two. So this will become dk minus 2 times, now we multiply x power minus n plus k. So this is what, so this together, this and this is this, plus you have 1 minus 2n d1 x power minus n plus 1 equal to 0. N is from 1 to 3 onwards. Now what you do is you simply multiply both sides x power, left hand side equal to 0. So this is what you have, you simply multiply x power n both sides. if you do this, what you get the same. So, I multiply, if I multiply 2n, so what you have is 2n here, and here this goes, this is simply x power k, and here is simply x. Okay. If you simply multiply, this is what you get. So, now this is the equation now. So, from this you have to calculate all your dk and a, the unknown constants. So, how do I do this? So, if you look at this series, it is starting from x2, x square, x3 and so on. Okay. So, starting from x square and so on. So, we start with and here and this one is starting from 2n plus 2, 2n plus 4, 2n plus 4 x power, this is the coefficient, this is x powers are 2n plus, n is fixed. Once you fix n, anything here, what you have is x power 2n plus 2 and x power 2n plus 4 and so on. Okay. This is something bigger, this is x power 2n, this is the coefficient of x power 2n here. So, lowest powers are x, first of all x, you have a x term. So, equate the coefficients. If you equate the coefficients, coefficient of x power 1 equal to 0, this will give me d1 equal to 0 first of all. Okay. What are the other terms? X square. So, 2, 3 up to, you can go up to 2n minus 1, because the next terms are 2n minus 1. So, 2n is here, 2n plus 2 is here. So, 2n minus up to 2n minus 1 I have to take only from here. Okay. So, coefficient of x square equal to 0 will give me, what do you get? So, d2, so x2, so k equal to 2, 2 is d2 equal to, this is 0 minus d0 divided by k equal to 2. So, you get 2 divided by 2 minus 2n. So, 2 square 1 minus n. So, if you can make it plus n minus 1 you can write. Okay. Again, so coefficient of x cube equal to 0 will give me d3 will be in terms of d1. So, d1 is 0. So, it will become 0. So, implies all d5, d7 up to d2n minus 1 equal to 0. Okay. And what happens to d4? So, you can calculate, say x power 4 equal to 0, x power 4, coefficient of x power 4 equal to 0. If you make it equal, so you get d4 as d0, you just calculate. So, d2 divided by something. So, d2 you already know from here, if you substitute you will see that d0 divided by 2 power 4 into 2 factorial n minus 1 n minus 2. So, this is what you will get. So, from this inductively you can write. Okay. So, from this, and you may have to calculate d6, you try to calculate d6 and put it in this form. From that you can see the trend and you can write d2n. So, how long you can go? You can only go 2n minus 1. So, 2n minus 2. So, let us write 2 n minus 2, that means 2 into n minus 1. Okay. 2 into 2, 2 into it n minus 1. This I am directly I am writing. So, d0 divided by 2 power 2 into n minus 1 into n minus 1 factorial square. This is what you will see. Okay. This is because you see that this is because d2l minus 1 for any l. Okay. This if you write it, what you see is d0 divided by 2 power 2l minus 2 l minus 1 factorial and n minus 1 n minus 2 unto n minus l minus 1 l, that is l plus 1. So, this is what. So, this sum when l equal to n minus 1 it becomes n minus 1 factorial. So, you get along with this l equal to n, you see that this will be square of this factorial. So, this is what you see. So, l you can, if you want, you can write like this, l equal to 2, 3, l equal to 2 if you put d2. So, you have a d2. d0 is anyway arbitrary, we did not find. So, 2, 3, 4 and so on n minus 1. Okay. So, because of this you can see this one. So, I found all some coefficients in terms of d0, some odd coefficients here are 0 up to 2n minus up to 2n minus 1. So, only from here I picked up. Now, for 2n, what is the value of 2n? So, 2n you have to pick up from here also and here. So, coefficient equation of coefficient of x power 2n equal to 0. If you do this one, what you see is a n divided by 2 power n minus 1 into n factorial. So, that is from here, that is the coefficient, plus now you can pick up from x power 2n. X power 2n is k equal to 2n. So, this will not contribute. What you get is d 2n minus 2 equal to 0. So, this will actually give me a equal to minus d naught. So, I know that my d 2n minus 2 from here. So, if you substitute and directly if you write, you see that is going to be d 0 divided by 2 power 2n minus 2 and then n minus 1 factorial square, that is my d minus of this, and you have into 2n minus 1 into n factorial. So, this will give me a n is there. So, you have a n here. So, that comes down. So, that is what is there. So, you have a minus, finally you see that. So, this n goes, n minus 1 factorial, that 1 factorial goes. So, you have 2 power n minus 1, okay. So, 2n minus 2. So, n minus 2 n minus 1 n minus 1 goes. So, you have n minus 1 and you have finally n minus 1 factorial. So, this is what you will see as your a, okay. Now, what else you can do? So, this coefficient is gone, okay. This will not contribute, this we have taken care. Now, you have to go with this and from picking from here. So, when m equal to 1, coefficient of x power 2n plus 2, okay, 2n plus 2, coefficient of x power 2n plus 2 equal to 0. If you do this one, what you see, well, you can also, so but here from here, but 2n plus 1 maybe you can pick up from here, okay. So, that is simple. So, coefficient of x power 2n plus 1 equal to 0 first of all from this, from the last this series if you do, there is basically x equal to 2n minus 1, okay. So, if you write that actually, so I will write directly. So, 2n plus 1 d 2n plus 1 plus d 2n minus 1 equal to 0, but we know that d 2n minus 1 is 0. So, that makes it d 2n plus 1 equal to 0. So, implies d 2n plus 3 and so on, everything is 0. So, d 2n plus 5, all that will be 0, okay. So, that is why you will only look at 2x 2n plus 2 x 2n plus 4 and so on. So, if you do this now x 2n plus 2, what you see is minus n plus 2. So, that means I picked up now from here one term and here one term. So, together if you write, you see that 2n plus 1 n plus 1 factorial plus 2 into 2n plus 2 d 2n plus 2 plus d 2n equal to 0. So, this will actually give me d 2n plus 2 in terms of minus d 2n 2 square n plus 1 n plus 2 2 power n plus 1 n plus 1 factorial. Okay, so, this is one, but you see that so far we have all that coefficients are in terms of d naught, but this one is in terms of d 2n. Okay. And similarly, coefficient of x power 2n plus, let us make it general terms, 2m equal to 0. So, m equal to 1 we have seen here. Okay. If I choose this, if I see this as a general term, m equal to 1 we have seen this one, okay. This is for m equal to 1. So, now for m equal to 2, so in general if you write minus 1 power m 2m plus n divided by 2 power 2m plus n minus 1 m factorial into m plus n factorial plus 2m plus n 2n d2m plus 2n d2m plus 2n minus 2 equal to 0. So, this is what is the general coefficient here. So, you take the x power 2m plus 2n and here now put k equal to 2m plus 2n and collect these 3 terms, that is what we have here. Okay. Now, m equal to 1 we have seen, this is what you get result, m equal to 2 what you get is, I am writing directly. So, if you will see m equal to 2, so you will see that d2n. So, you can see that d2n m equal to 2, you will see that d2n plus 4. What you see is finally this is only way, this only coefficient m equal to 2 is 4 minus 2. So, 2n plus 2. So, you have d2n plus 2 you have from here. Make use of this here and then finally you see that d2n plus 4 will be d2n divided by 2 power 5 n plus 1 n plus 2 minus 1 divided by 2 power 4 plus n plus 1 factorial into 1 plus n plus 4 divided by 2 factorial 2 square n plus 2 whole square. So, do not worry about all this. So, what you are seeing is d2n plus 2 is in terms of d2n, d2n plus 4 will be in terms of d2n. Okay. Like that you will get. So, d2n plus 6 will be in terms of d2n, something else you will get. Okay. Conventionally if I choose my d2n, so you know that, right, in the power series method you can if you want to choose, if you have a C0 of some power series you get, this is a constant. So, you can choose this as a constant number, but if you write everything in terms of some Cn into some power series, okay, so known power series into Cn, if this is your solution you have to choose, you can choose your Cn depending on n. Okay. Cn can be like 1 by n plus 1. So, this is the function depending on n, like that you can choose. So, using that, so if I choose conventionally, this is our if d2 is chosen this way, d2n is conventionally chosen in this way. So, 2 times n plus 1 divided by 2 power n minus 1 into n minus 1 factorial, this just I am writing. Okay. So, 1 divided by 2 power n plus 2 n plus 1 factorial into 1 plus half plus 1 plus n up to 1 by n. So, this is what, if I choose this is what is convention, okay, conventionally chosen constant, that in terms in as d naught, you can always choose d naught, any constant times that is also fine, it depends on n. So, this is how if you choose, okay, then your d2n plus 2 will be in terms of d naught, again d2n plus 4 will be in terms of d naught, everything in terms of d naught, and earlier you have seen a also in terms of d naught, and you have seen that d2n minus 1 also in terms of d naught, everything in terms of d naught. So, this implies you have your y2, whatever you get y2 as some power series times d naught. Okay. So, choose your d naught as 1, finally because the constant, this y2 of x is what you get is your yn of x. So, this is what is the Bessel function of second kind. Okay. So, this is how you get the second solution in the case of root difference is a integer, positive integer, and in that we avoided the case 2 alpha equal to 0, that we will see in the next video, and what we have seen is only 2 alpha equal to 1, 2, 3 and so on. So, that is actually odd integer case is simpler, and even integer case, that is when alpha equal to 1, 2, 3 onwards, that is alpha equal to n is from 1 to 3 onwards. We have seen the second solution y2 conventional constant, if you multiply final solution what you get is a Bessel function of second kind. Okay. So, you just do not worry about this horrible calculations, just the procedure you understand, you are not going to do any problems on this. Just try to watch this video, just understand how the Frobenius method works for the Bessel equation in the second case. Okay, we will see the third case, that is when the difference between the roots is 0 or same. 0, that means the roots are same. That is possible only when n equal to 0 case. Okay, so that we will see in the next video. Thank you very much.